Let me start with drawing the figure. So I'm actually going to piggyback off of this a little bit, which is why I haven't erased it entirely. So, you know, you look at this expression, it looks super complicated, right? Yes, everyone agrees it looks complicated. So what I'd like to be able to do is come up with some limiting case where I can simplify this expression. So, you know, physically what we are looking at is this, right? Interaction of a rod with a ball. So by limiting case, this is what I mean. I could make this ball very, very far away, or I can make it very, very, very close. So which limiting case do you want to look at? To try to make this expression simpler. Very, very far away? Yeah, if you do very, very far away, I won't write it down because it looks pretty simple. If you say D is much, much bigger, then you look at this expression, see what you can ignore. This is what you can ignore in that case, right? So the denominator becomes D times the square root of D squared, or, you know, that's just D squared. So in that case, what you get is you get Coulomb's law back. Because what you have is K times the lambda times L, that's the amount of charge in the rod, times Q, amount of charge in the point charge, divided by distance squared. Which is, you know, what you would have expected, which is what you should get. Now, would this also simplify if you said that this charge is very, very, very close? Let's see what happens. I would actually like to draw it in a different way. Rather than saying that the charge is very, very, very close, I'll say charge remains here, but the rod becomes very long. That's an equivalent way of saying it, right? So I can consider the interaction between infinite rod and point charge. So the rod becomes infinitely long, but it's going to have the same charge density lambda. So, you know, if you get the entire rod, it'll be infinite amount of charge. So I won't go there. And for this infinitely long rod, I say there's a charge Q here at some finite distance D, and ask the question, what is the force? Well, I take this expression, and what limit am I taking? Like so, you know, I'm going to take one of the quantities, let it go to infinity. What am I letting go to infinity? Yeah, so I'm taking that. I'm taking the limit of L going to infinity of all of that expression. K lambda Q L over D square root of D squared plus L squared over 4. All right, I don't know what to do with that. Let me ignore it for now. I think I know what to do with this, so let me do that. What happens with this expression? Is there something you can ignore? What can you ignore? That's the infinite quantity. You can't ignore the infinite quantity. That's the thing. Yeah, D becomes infinite, you know, much, much smaller in comparison. So when it's being added to something infinite, you can ignore it. So you have square root of L squared over 4. So this whole quantity is actually equal to L over 2. Right? So, this L cancels with that L, which is good because I don't want anything going infinite in my final expression. So I actually end up with a finite amount of force. Let me write it here. I get force is equal to K lambda Q times, I've divided by 1/2, so there will be 2 K lambda Q divided by D. I get this very simple expression for the interaction between infinite rod and a point. And believe it or not, you will see this expression again. We are going to redo this sometime next week in a different way with a different context. The way we did it is the hard way. I will try not to do it this way again.